All right, so in this video, we're going to go ahead and take the Laplace transform of this function f1 of t here. Basically, it's just a scaled and shifted version of the unit step function. If you remember, the unit step function basically is a function of t that has a value of 0 everywhere before 0 and a value of 1 everywhere after 0, and it's just written as u of t. That's an ugly u of t. Still pretty ugly. Anyways, this is the unit step function. And then this here, this f1 of t that we're looking at, is a time shifted, right? It's shifted by t in the time domain. And it's also a scaled version of u of t. So if we multiply u of t by a value a, we might get a little bit taller, we might get a little bit smaller. And we shift it by t, then that's our signal here, right? This is just shifted and scaled version of the unit step function, okay? So keep that in mind as we go through this. But we want to take the Laplace transform. So my f1 of t is equal to a times u of t minus big T. And I want to take the Laplace transform of f1 of t, which will give me f1 of s, right? A new function of s. And that's going to be, by definition, the integral from 0 minus up to infinity of a u of t minus t, right? This is my f1 of t multiplied by, so if we go back here, it's f of t multiplied by e to the minus st, right? So I multiply this by e to the minus little t, and then I integrate that with respect to time. And that's what we get, okay? This is our integral, so now we have to solve this in order to find f1 of s, okay? So let's go ahead and do that. So I can say my f1 of s is basically equal to, let me pull the a out, the integral from 0, the minus really doesn't matter, we can just call it 0 for now. It's really there for initial conditions. U of t minus t times e to the minus st dt. And what I want us to take into consideration here is that u of t minus t is basically 0 all the way up until the value t. So this integral from 0 to infinity, we don't need to account for anything from 0 to t. So instead of writing this expression, I could write it as, you know, the integral from 0 to t of 0 plus the integral from t to infinity of e to the minus st dt, right? Because that's basically what it is. From 0 to t, we're integrating and we're getting nothing, right? There's no area here. It's just 0. So this whole thing goes to 0. And then from t out to infinity, we're integrating the unit step function because I factored out an a. Of course, we could throw this a back in here at this point, and it would be the same. But let's just keep going with this now. So we can say that this is equal to a times the integral from t to infinity of e to the minus st dt. And so when we take this integral, this should be pretty straightforward. E to the minus st is just going to give us a negative 1 over s e to the minus st. And then I integrate from t to infinity. And so I can plug in here a times negative 1 over s e to the minus s times infinity, right? Minus a negative 1 over s, so I'll just put plus 1 over s e to the minus s big T. Well, e to the minus s times infinity is the same thing as saying 1 over e to the s times infinity. And e to the infinity is huge. That's going to be basically make this whole thing go to 0, right? So I can say that this entire term goes to 0, and I'm left with a times 1 over s e to the minus s times big T. And that is my function f1 of s. And so I can box that, and that's the Laplace transform of my shifted and scaled version of the unit step function. Of course, if we let t equal 0, right, with no time shift, and we let a equal 1, so no scaling, this entire e term goes to 1, and the a goes to 1, and we're just left with 1 over s. So the Laplace transform of u of t, that's basically just the unit step function, right? If we allow a to go to 1 and t to go to 0, the Laplace transform of u of t is just 1 over s. And that is the value for the Laplace transform of the unit step function, which is exactly what you will see in the table when we get there later. Okay, so of course, this was what we were after. We were after the Laplace transform of this particular signal, but I think it's important to note that this particular signal, if we let t go to 0 and a go to 1, we just get u of t, which I have here. And so the Laplace transform of u of t is just 1 over s. And that's something that we're going to use quite a bit because our circuits are going to have unit step inputs, right, where they're at 0 and then they jump up to a value at time t equals 0. Maybe if we just let there be no time shift, but we do want the scale, we can see that. So if this was something like 5 volts or 5 for A, then this would just be 5 over S. Okay, and so this is going to be a really useful result. I'm going to go ahead and end this video here, and in the next video, we'll do another example of another function solving for the Laplace transform.